Hello, in this video we're going to continue talking about graphing potential energy, but now we're going to add some more details to it. We're going to look at special points on the graph and what that means for forces. We'll also look at putting on total mechanical energy along with kinetic energy. So we're going to use up most of our slide for this. We'll draw an x-axis and an energy axis, and I'm just going to call that an energy because we're going to put not just potential but also mechanical and kinetic on there. Horizontally we'll do x, and let's come up with a fancy shape for our potential energy. I'm going to give it a bunch of wiggles, but they are intentional. Don't just draw something randomly wiggly. There is some method to this craziness. Alright, so I want it to come all the way down, and then up, and then down, and then up, and then down. Okay, and if I did that right, these should be at the same height. That's what I'm aiming for, at least. Because I want to put the total energy right there. So it's just hitting those points. And so that'll be the total mechanical energy. Okay, and all right, I think that looks good. I want to get a bunch of features on this graph, which is why I'm being so picky with the shape I draw. So this is theoretically, this black line is theoretically what the potential energy would be for a system, and it's probably something kind of complicated if it has all these wiggles in it. Probably not just gravity and a spring, but something more so. And here we have our total mechanical energy. It's possible for the system to have a total mechanical energy that's cutting through your potential energy graph. So even though in principle a system could have this much potential energy, it doesn't have enough total energy to ever get there. So an example of this is, imagine you have, say, like a cowboy hat. It's the best thing I could think of right here. So you got a cowboy hat with some kind of wacky shape, all right? And you've got a marble rolling around in that cowboy hat. Let's say it's rolling around back and forth on this little divot on the top of the hat, right? And here's someone's head. It's rolling around back and forth. In theory, this could have more gravitational potential energy. It could have more potential energy if it was up here, but it just doesn't have enough total mechanical energy to ever get up there. That's what I mean by this. And so in some sense, the curves on this graph are kind of like the curves on a crazy hat. So bear with me for a moment. All right, so then we can also add in the kinetic energy. Like we saw in an earlier video, the kinetic energy is the difference between the total mechanical energy and the potential energy. So this difference is the kinetic energy. And there are some places where the kinetic energy is equal to 0, and there are some places where the kinetic energy is seemingly negative. What that really means is the object can't actually be there. So if we come back to our little marble here rolling around on someone's hat, the marble doesn't have enough energy to ever be here. So if I ask, for example, what's the kinetic energy over here, that's not a good question because the marble isn't over there and can't be over there. It's the same kind of thing on this graph. So in fact, we have places where things could get stuck. If I had a particle over here, so what would happen is if I put that particle, say, right here, it would have some kinetic energy and it would move down, or rather it would move in the positive x direction, getting less and less kinetic energy until it gets to right here. At this value of x, that particle now has 0 kinetic energy and it can't go anywhere else. It's stuck. Okay? And so that's called a turning point. What that means is the particle can't keep going to the right. It has to turn around and go back to the left. And as it moves to the left, this graph is getting deeper. It's got more and more kinetic energy. It's going faster and faster. Now it's slowing down until it stops. And then right here, there's no kinetic energy. So that's also a turning point. There are some other turning points on here. Well, there's one more turning point on here, right here. So we'll say turning points. Okay. So if we had a particle over here, it could move back and forth, but it would get stuck here and have to turn around. So these are entirely analogous to sort of picturing what's happening to a particle rolling around in a valley, or a ball rolling around in a valley. Now this spot here is a little bit different. It's not quite a turning point. A particle could make it past and head off to the right, although that point must be special in some way. So let's give it a different color. That's called an equilibrium. It's a particular type. It's an unstable equilibrium. So unstable because if I put a particle there, even though in principle it could stay there without having to move, it has zero kinetic energy, but if you bumped it either direction, it would move. That's what makes it unstable. Let's contrast that to a stable equilibrium. We have one of those over here. If I put a particle there, it would have zero kinetic energy, and it, in fact, wouldn't even be allowed to move either direction because it would have to have an impossible negative kinetic energy. It just stays there. So it's very stable. Okay, there's one more feature we can add to our graph, which is the direction of the force. So anywhere along here we have a force, and we saw in the previous video that you could figure out what the value of the force is by taking the derivative of this graph of potential energy, which actually I realize I never labeled. There we go, just for completeness. So if we think about it right here, the slope of this graph is negative, which means that the force would be positive. Remember, force is equal to the negative of the derivative of the potential energy. Positive means positive x-axis, so all the way up until this equilibrium point, the force points to the right. And then here, this segment, the force is negative, so it points to the left. Not that you could have a particle out here, but that's the direction the force would be if the mechanical energy were high enough that the particle could be there. If we look at this over here, the force points to the right until we get to the middle of this. Here we've got force pointing to the left, pointing to the right, pointing to the left, pointing to the right, to give you an idea of what direction something would be forced. Okay. So, at first glance, this looks really complicated. I realize that. But if you can wrap your head around what's actually going on here, potential energy becomes a much more useful quantity. In fact, this kind of drawing graphs like this is used a lot in quantum mechanics, and I realize that most of you probably aren't going to go on to study quantum mechanics, but it is a very powerful tool. That's why they use it. And so it can be helpful to you to be able to visualize in multiple ways how systems works. And this is one way to visualize. If you prefer the more physical things rolling around on someone's hat picture, great. In reality, they're actually very similar to each other. All right, I'll see you in the next section.